Zero-Base Guide to Mastering General Relativity. Believe it or not, first take a look at this thought experiment that completely changed the course of human science. Inside a small room isolated from the outside world. After measuring your weight, you find that it hasn't changed at all and is still 80 kilograms. So now please judge where this room is located. Which of the following places is it? 1. The room is on the surface of the Earth. 2. The room is inside a spacecraft accelerating through space, with an acceleration equal to that on Earth's surface, about 9.8 meters per second squared. 3. It's impossible to tell. Let's see whether your answer beats that of more than 99% of people. Let's rewind time to the early 20th century. Back then, a small clerk working at the Swiss patent office happened to glance out a window and see a janitor standing on a ladder. In a flash of inspiration, he asked himself a deceptively simple question. If the janitor slipped and fell off the ladder, and if we ignore upward air resistance, would the janitor feel the gravitational force of the Earth acting on him before he hit the ground? Imagine losing the support of the ground. As he accelerates downward, the janitor would be in complete weightlessness and would be unable to feel Earth's gravity. The reason is that the object's accelerated motion cancels out the Earth's gravitational pull. By intuition, the young clerk felt that behind this simple question lay some astonishing truth. After all, accelerated motion produces inertial forces. For example, when a rocket crazily accelerates upward, it creates a downward inertial force that pins the astronauts firmly to the floor. So when the janitor accelerates downward, an upward inertial force will be produced. Yet it seems that this, too, is cancelled by the downward gravitational force. It appears that gravity and inertial force can cancel each other out. So what exactly is the relationship between inertial force and gravity? Can they substitute for one another? The great thought experiment at the beginning started to take shape in the clerk's mind. After pondering it again and again, he speculated that for a closed small room, even if it were located in a spacecraft far away from Earth, as long as the spacecraft's acceleration during flight had the same magnitude as the acceleration produced by gravity on Earth's surface, then the inertial force generated inside the small room, and the gravitational force on Earth's surface would be completely indistinguishable. Looking at the 80-kilogram reading, the person inside the small room could fully believe that they were standing on Earth's surface. Inertial force seemed to have completely replaced gravity. In the end, the young clerk arrived at a bold conclusion. The inertial force formed in an accelerated reference frame and the gravitational force around celestial bodies have exactly the same physical nature. They are the same force and are completely equivalent. Thus, the equivalence principle, one that would completely change the course of science, was born. This great little clerk, of course, was Albert Einstein. At that time, only a few years had passed since he published Special Relativity. Einstein was tossing and turning every night, troubled by the fact that special relativity could not explain accelerated motion and gravity. The discovery of the equivalence principle showed him the only way forward, and he declared it to be the happiest thought of his life. And next, a rotating disk and a beam of ordinary light that Einstein imagined would completely lift the veil on the mystery of gravity and inertia. This rotating disk later became known as the Einstein disk. Imagine a circle lying in a plane. If we make it rotate at a constant speed, since the circle is a geometric entity in space, its geometric structure must inevitably be affected by the length contraction effect of special relativity during rotation. Let's take a look at how pi, that is, the ratio of circumference to diameter, deviates from its standard value of 3.14159925 during rotation. If the rotational speed of the circle is relatively slow, you might not notice any obvious change in pi. But what if we make the tangential speed of the circumference approach the speed of light? For example, reaching 99% of the speed of light. What would happen then? Since every point on the circumference is moving at 99% of the speed of light, according to the length contraction formula along the direction of motion in special relativity, the circumference will shrink to 14.11% of its original length. Meanwhile, the diameter is always perpendicular to the direction of rotation, so its length does not change. This causes pi to shrink proportionally, down to 0.4432, due to the shortening of the circumference. And as the rotational speed of the circumference gets closer and closer to the speed of light, pi will get closer and closer to zero. At this point, the geometric structure of the Einstein disk is about to collapse. What kind of geometry could possibly shorten a circle's circumference while keeping its diameter unchanged? Einstein quickly thought of a curved two-dimensional surface. Imagine drawing a circle on the curved surface of the Earth, with the North Pole as the center. The diameter would bend downward along lines of longitude on the Earth's curved surface. The diameter would become a set of curves extending outward from the center and perpendicular to the circumference. If you compare the circumference of a circle on Earth's curved surface with that of a circle on a flat plane that has the same diameter length, the circumference on Earth's surface would definitely be shorter, and pi would correspondingly become smaller. Or you can understand it this way: if the circumference is kept constant, while the diameter gradually bends into a third spatial direction, then pi will begin to shrink because the diameter increases. At this moment, Einstein finally realized that the rotating circle was no longer a planar geometric structure. In fact, it had already become non-Euclidean geometry. That is to say, the plane on which the circle originally lay would bend in a certain direction due to rotation. But note this carefully: the direction of this bending is actually the time direction in four-dimensional spacetime. Next, Einstein thought of the most crucial point: the bending of spatial geometry is accompanied by the appearance of inertial forces. For example, on the two-dimensional surface rotating along with the circle, an inertial force appears, what we usually call centrifugal force. If you stand on the rotating two-dimensional surface, the farther you are from the center, the greater the outward centrifugal force. The closer you are to the center, the smaller the outward centrifugal force. On the other hand, the farther you are from the center, the greater the degree of curvature of the two-dimensional surface. The closer you are to the center, the smaller the degree of curvature. Based on this, Einstein boldly conjectured, the appearance of inertial force must be a kind of surface phenomenon. Its underlying physical essence is actually that space has become curved. When flat space becomes curved, inertial forces that we can perceive appear. If we use curvature to qualitatively represent the degree of spatial bending, then the greater the curvature, the greater the inertial force. The closer the curvature is to zero, the smaller the inertial force. To verify his conjecture, Einstein came up with a brilliant idea: use the trajectory of light in a vacuum to test whether space is curved. Since the speed of light is the fastest speed in the universe, light in a vacuum must travel along the straightest and shortest possible path. So in a vacuum region filled with inertial forces, if a beam of light is emitted at an angle perpendicular to the inertial force, and if the essence of inertial force truly is the curvature of space, then the trajectory of the light must take the shape of an arc. But if inertial force has nothing to do with spatial curvature, then the trajectory of light in an inertial frame would remain a straight line. Of course, in Einstein's time, this was still only a thought experiment. Now imagine being inside a spacecraft accelerating straight upward. If a beam of light is fired horizontally, then after the light is emitted but before it reaches the wall, the entire small room is still accelerating upward, but the speed of light cannot increase. The acceleration of the entire room is meaningless to the speed of light. By the time the light reaches the wall has already moved upward by some distance. So inside the small room, the trajectory of the light will inevitably appear to bend downward by a certain angle. If we magnify this deflection angle, we can clearly see that, within this inertial frame of the small room, the path traveled by the light is no longer a straight line, but a curve deflected in the direction of the inertial force. And the incredible fact is that this curve is exactly the straightest possible line between the emission point and the point where it strikes the wall. It is also the shortest path between the 2 points. If you forcibly draw a visually straight line between these 2 points, it may look shorter than the curve taken by the light, but in fact, in the curved space of the small room, the visually drawn straight line would actually be longer and more bent, because light always moves along the shortest path between 2 points. At this point, Einstein saw that behind inertial force there truly lay the curvature of space. Then, according to the equivalence principle, gravity must also be the result of spatial curvature. From that moment on, Einstein finally revealed the essence of gravity. It turned out that the reason objects generate gravitational attraction is that their existence causes the surrounding space to become curved, and an object's mass is a measure of the magnitude of inertia. Just like on the Einstein disk, the farther you are from the center, the greater the acceleration, and thus the greater the inertial force, and the more severely space is curved. Likewise, the greater an object's mass, the stronger its gravity, and the more severely space is curved. To borrow a line from Wheeler, mass tells spacetime how to curve, spacetime tells mass how to move. Modern physics believes that the essence of gravity is not just spatial curvature, but the curvature of the entire four-dimensional spacetime, because any object, including light, in four-dimensional spacetime actually always moves along the shortest path between 2 neighboring points. Then the distortion of space will inevitably bring about the distortion of time. If, starting from the thought experiment at the beginning of the video, you followed Einstein's journey, and truly understood the spatial curvature behind gravity, then congratulations, one of your feet has already stepped into the doorway of modern physics.